Hello everyone, so welcome back to CEBack's tutorial channel, and our topic for today is all about the overall buckling of compression members. So kasi last time, ang napag-usapan lang natin doon and na-solve na type of problem is under lamang sa flexural buckling. Though na-introduce na rin namin or nabanggit na rin namin sa introduction ng chapter 4 yung dalawa pang type ng buckling sa compression member, which is the torsional and the flexural-torsional buckling. So, balikan lang ulit natin yung meaning ng flexural buckling. So, in flexural buckling, it is a deflection caused by bending or flexure about the axis corresponding to the largest slenderness ratio. Okay? So, compression members with any type of cross-sectional configuration or cross-sectional area can fail in this way. Okay? So, ibig sabihin lang nun, kahit ano pang section yan, okay, mag-fail pa rin under sa flexural buckling. Okay? The number 2 is the torsional buckling. So this type of failure is caused by twisting about the longitudinal axis of the member. It can occur only with doubly symmetrical cross sections with very slender cross-sectional elements. So standard hot rolled shapes are not susceptible to torsional buckling. Okay? So ibig sabihin yung mga sinob natin na na wide flange, yan, yung mga standard hot rod shape na yan, yung mga wide flange, HSS, yan, are not susceptible to torsional buckling. But members built up from thin plate elements may be and should be investigated. Okay, yung mga built up member. And sa torsional buckling kasi, not usually yung malakas or yung mabilis na mag-fail under sa torsional buckling is yung merong cruciform shape. Okay, yan. So, yung cruciform shape is almost cross or cross shape. So, yun yung mag-undergo sa torsional buckling. Ay, yes, ito pala yung natin, flexural buckling. And alam naman natin kapag flexural buckling, ganito ang niya, pag-buckle niya or pag-bend. Okay? And then, this is torsional buckling. So, pinakita dito na cruciform yung shape. So, yung last, okay, is yung flexural-torsional buckling. So, this type of failure is caused by a combination of flexural buckling and torsional buckling. So, mangyari dito, yung member natin will bend and twist simultaneously. So, this type of failure can occur only with unsymmetrical cross-sections. Okay? Both those with one axis of symmetry. So, yung mga example ng one axis symmetry is yung channel. Hindi ba? Saka yung mga structural tees. Okay? Kasi di ba kapag channel, ayan, ito yung ating y and x-axis. So, yung ating axis of symmetry is sa x-axis, di ba? Kapag naman t, okay, yan yung ating t, yung axis of symmetry niya is sa y. So, one axis of symmetry lang yan. Okay, then double angle shapes, of course, and equal leg single angles. And those with no axis of symmetry. So, yung lahat ng mga with no axis of symmetry, mag-undergo pa rin siya sa flexural-torsional buckling. And example ng no axis of symmetry is yung unequal leg single angle. Yan. And paano mangyayari yun? So, ganito yan. Okay? So, magbe-bend siya. Then, at the same time, mag-twist. Yan. Okay? Para natin ang kulay red. Yan. Magbe-bend siya, tapos mag-twist siya. Kaya tinawag siya as flexural-torsional buckling. Okay? Actually, yung isosolve lang natin dito is yung sa flexural-torsional buckling. Kasi kapag compression member, napaka-rare na gumamit ng cruciform shape, okay, as compression member. Kaya hindi na natin itatakil. Actually, kay William T. Segui, hindi rin niya tinakil yung yung pagsosolve ng compression member under sa torsional buckling. So, ang in-example lamang niya dun is yung compression member under sa flexural-torsional buckling. So, take note, sabi rito sa flexural buckling, all compression members with any type of cross-sectional configuration can fail in this way. So, ang mangyayari, i-investigate natin yung member, una sa flexural buckling, then pangalawa sa flexural-torsional buckling. So, ibig sabihin, makakakuha tayo ng dalawang nominal strength or nominal capacity ng ating member, then pipili tayo ng mas mababang nominal strength. So, malaman natin kung sino yung nag-govern, kung flexural buckling ba or flexural-torsional buckling. Okay? So, based sa NSCP 2015 requirements, okay, So, sa 501.5 general provision, so ito yung kinat ko po doon sa introduction ng ating chapter 4. Kung naalala ninyo, okay, ito yan. Okay, so kinat natin siya. Okay, kasi, syempre, ang unang topic lamang natin is flexural-buckling. So, dito kasi sa 501.1, sinama-sama niya na lahat. So, basahin natin. So, sabi niya rito, the design compressive strength, okay, for LRFD, and of course, for the allowable compressive strength for ASD, are determined as follows. The nominal compressive strength na PN shall be the lowest value. Yun yung sinabi ko sa inyo, okay? So that is shall be the lowest value obtained according to the limit of flexural buckling, torsional buckling, and flexural-torsional buckling. Okay? So number 1, for doubly symmetric and singly symmetric members, the limit state of flexural buckling is applicable. Okay? So ano sabi niya rito? Para do sa doubly symmetric and singly symmetric, i-investigate daw natin yung member natin under sa flexural buckling. Then for singly symmetric and unsymmetric members and certain doubly symmetric members such as cruciform, yan yung cruciform shape or built-up columns, the limit states of torsional or flexural buckling are also applicable. Yan. Pero syempre, sa atin nga, ang example lang natin dito is yung under sa flexural and flexural-torsional buckling. And ganun pa rin, yung ating P sub C is 0.90 for LRFD and yung ating sigma sub C for ASD is 1.67. Then dito naman is 0.90. Okay? Then, syempre, doon sa una, sa flexural buckling, that is under sa 505.3. Okay? So, flexural buckling of members without slender elements. So, dito, okay, so, I think this is not 505.3. So, sorry, hindi ko lang siguro na-update to. Yan. 505.4 to. Okay? So, 505.4. So, under sa 505.4, compressive strength for torsional, yan, for torsional and flexural-torsional buckling of members without slender elements. Okay? This section applies to singly symmetric and unsymmetric members and certain doubly symmetric members such as cruciform or built-up columns with compact and non-compact sections, as defined in section 502.4 for uniformly compressed elements. So these provisions are not required for single angles, which are covered in section 505.5. So the nominal compressive strength, PN, shall be determined based on the limit state of flexural-torsional and torsional buckling. So, ganun pa rin naman ang ating PN. Ang PN is equivalent to FCR multiplied by AG. Ang mangyari lang, yung ating FCR is iba-iba. Depende sa kung ano yung ating type of member. So, for double angle and T-shape compression members, yung ating FCR is equivalent to, okay, FCRY plus FCRZ over 2H. Okay, multiplied by 1 minus square root of 1 minus, di ba napakahaba? Okay. Ayan, so, di ko siya babasahin. Kaya nyo na yan. Okay, so, basahin nyo na lang siya. Actually, pwede nyo rin naman siyang i-memorize para sa lahat ng mga nagpe-prepare para sa board exam. Pwede nyo siyang i-memorize, pero I think this code is talagang naka-include na sa inyong, examination papers. Okay, nandun naman yan, sigurado. Okay, pero, nung nag-review ako sa board exam, hindi ko maalalang may mga ganitong equations, okay? Ang tagal na kasi 2016 pa, pero ang madalas kasing lumalabas sa steel design and yung mga nireview talaga namin halos is sa beam, then sa connections, then yung mga shear stress, okay, bearing stress, mga ganyan. Ganun yung mga kadalasan lumalabas sa sa steel design. So hindi ko masyado maalala tong sa compression. Anyway, ayan. Para naman sa mga undergrad, ito yung para sa ating flexural, torsional buckling, and torsional buckling. Okay? So, sabi rito, ang ating FCRY taken as FCR. Okay? Dun sa ating equation 505.3-2 or 505.3-2. Or 3 pala, sorry. So, nasaan yun? Dito yun. Sa napag-usapan natin ng una. Ayan. So, equation 505.3-2 and equation 505.3-3. Okay, ayan. So, this is our FCR. Okay, so ibig sabihin, kung ang FCR natin is FCRY, ibig sabihin yung ating KL over R is magiging KL over RY. para makuha natin na yung ating FCR is in terms of FCRY. Okay? Sabi niya dito, ganun naman siya, di ba? Ayan. And ayan, ito. Yung ating KL over R is magiging KL over RY. Doon natin kukunin yung ating FCRY. Then yung ating FCRZ is equivalent to GJ over AG multiplied by R, okay, bar sub O squared. Okay? Then, number 2, for all other cases, okay, ibig sabihin, maliban sa double angle and T-shape, okay, for example, channel, yan, mga ganyan. So, yung ating FCR dito shall be determined according to equation 505.3-2 or 505.3-3. So, yun nga, ito. Okay? Pero, take note lang natin na using the torsional or flexural-torsional elastic buckling stress, ito yung gagamitin natin na FE. Okay? So, yung FE natin, for doubly symmetric members, FP is equivalent to pi squared E multiplied by C sub W over KZL squared plus GJ. Okay? Multiplied by 1 over IX plus IY. Okay? So, for, doubly symmetric members, para to sa, ito sa mga white planche, mga ganyan. Okay? Actually, sa white planche, puro yun talaga yun eh. Kapag white planche, more on siya, flexural-buckling talaga. Okay? So, yung tinutukoy dito na double symmetric members is kung ano ba yung mga double symmetric members? Siguro, double C-channel, mga ganyan. Okay, so doubly symmetric members yun. Okay? Then, for singly symmetric members such as channels, ayan, na kung saan yung ating Y is the axis of symmetry, yung ating FE is equivalent to FEY plus FEZ over 2H. Parang ganito rin siya. Okay? Pero ang mangyari dyan, imbis na FCR, FEY. Then, imbis na FCRZ, FEZ. Okay? So, this is only for singly symmetric members. Okay? Then, ayan. Yan yung ating gagamitin na equation for singly symmetric members. Medyo marami nga lang talaga siyang equation. So, kailangan nyo lang i-identify or i-distinguish kung under saan nga ba talaga yung ating member. Kasi dito, for double angle lang naman to at T-shape. Okay? Pero, for all other cases, okay, yung ating FCR naman kasi is manggagaling sa ating equation 505.3-2 or 505.3-3. Then, kailangan natin kunin yung FE. And then, ito, dalawa yung ating FE. Yung FE for doubly symmetric and FE for singly symmetric members. Yan. Just take note na dapat yung ating nandito, axis of symmetry is either sa Y or X. Okay, pwede pwede magbago yan. Pwede siya maging X. For example, yung orientation natin sa C-channel, saan ba? Okay, kasi sa C-channel, sa C-channel, yung axis of symmetry natin is X-axis, hindi ba? Ayan. So, yung, yung ating, rito, FEY is magiging FEX. Ayan. FEX yan. Okay, nagbabago yan. Okay? Then, letter C, for unsymmetric members. So, wala siyang kahit anong symmetrical section. Yung ating FE is the lowest root of the cubic equation. So, lowest root daw natin dito. So, makikita natin bakit siya naka-root. So, ibig sabihin, ito, naka-square siya eh. So, since naka-square to, tapos mamultiply pa natin dito, so, cube root na yan. Hindi ba? So, naka-raise na yan sa 3. So, ibig sabihin, tatlo yung makukuha natin ng FE rito. Okay, so yung pinaka-malit daw na root ng FE, yun yung kukunin natin na FE. Okay? So, sa lahat ng mga napag-usapan nating equation, ito yung mga notations nila or meaning. Ang AG, of course, is the gross area of the member in millimeter squared. CW is the warping constant, millimeter squared, millimeter to the 6 power. Okay, ang CW or warping constant, pag sinabi nating warping constant is the parang ability or parang specification, characteristic ng isang member to bend. Okay? So, ibig sabihin kasi ng warp is to bend. Okay? Then yung ating R bar sub O squared is equivalent to XO squared plus y sub o squared. Okay? Ang x sub o and y sub o is the coordinates of shear center with respect to the centroid. Okay, so nung nag-search ako kung paano kunin kasi yung shear center, marami pang kailangan gawin. Okay, magi-integrate pa, mga ganyan. Pero kapag kasi T, ang shear center niya is ando sa sa intersection ng center line ng ating flange and web. Okay, so andun yung niya, shear center. Anyway, I think yung shear center naman is hindi na ipapahanap pa sa mga problem. So, i-given na lamang yan sa mga problem. Okay? Then yung ating R bar sub O is the polar radius of gyration about the shear center. And then, ang H natin is equivalent to 1 minus x sub O squared plus y sub O squared over R bar sub O squared. Then, ang FEX natin, ito, yan. Ang FEX natin is pi squared E over KXL over RX squared. Then, ang FEY natin is pi squared E over KYL over RY squared. Then, ang FEZ natin is pi squared E multiplied by CW over KZL raised to 2 plus GJ multiplied by 1 over AG R bar sub O squared. Na kung saan yung ating G is the shear modulus of elasticity of steel. So, bakit nagkaroon tayo dito ng shear modulus? Kasi meron tayong torsion. Okay? Kung babalikan ninyo ang ating strength of materials under sa chapter 3, torsion, yung torsion kasi is nakikreate ng shear stress sa ating cross-sectional area. So, since meron tayo ditong shear stress, so kailangan natin gamitan ng shear modulus of elasticity of steel. Or any type of material. Okay? And of course, Ix and Iy is the moment inertia about the principal axis. J is the torsional constant, millimeter to the fourth. Kz is the effective length factor for torsional buckling. Okay? And Ry is the radius of gyration about y-axis, millimeter. So, user note, for doubly symmetric I-shape, and for doubly symmetric I-shaped sections, CW, okay, magkaiba ang I-shape sa sa wide flange. Okay, magkaiba yan. Kasi ang I-shape, ganito yung shape niya. Ayan. Hindi wide yung flange. Kaya nga I, di ba? Ayan. Kasi ang wide flange, from the word itself, wide, okay, sabihin, malapad yung flange niya. Okay? So, yung ating CW may be taken as IY, okay, or yes, Iy multiplied by h sub o squared over 4, where h sub o is the distance between, okay, the flange centroids in lieu of a more precise analysis. So for T's and double angles, omit term with CW when computing FEZ and take x sub o as 0. Ayan. Okay, so nasan ba yun? Yung ating x sub o, ayan. So, sabi niya dito, for T's and double angles, yung x sub o kasi natin is magiging equivalent to, to 0. Okay, so magiging, equivalent to 0. So, ano mangyari doon? Okay, I think, omit term with CW when computing FEZ. Yung FEZ, Okay, and take x sub o as 0. Siguro, kapag nag-solve na lang tayo ng problem, doon natin may encounter itong sinasabi niya. Okay? Sige. Ayan, so, ito yung introduction ng natin. Overall buckling of compression members. Kung saan pinag-usapan natin yung torsional buckling and flexural-torsional buckling. Ayan, di ba napakaraming equation nga lang. Pero don't worry, iisa-isa natin yung mga equation na yan kapag nag-solve na tayo ng problems. Basta wag lang kayo magpapalito. Okay, kasi di ba pinakauna naman nating alam under flexural buckling or sa compression member, ang ating PN or ating nominal strength is equivalent to FCR multiplied by AG lang naman. Hindi ba? Ganun lang siya kasimple. Na kung saan, ang AG di naman nagbabago. Tama ba? Ang nagbabago lang is yung FCR. So, yung ating FCR is possible na manggaling, number 1, sa flexural buckling, hindi ba? Then, number 2, sa torsional buckling, and number 3, sa flexural-torsional buckling. Yan, then katapos nun, pipili lamang tayo ng ng mababang PN. Yun na yung kanyang nominal, okay, or available strength for that specific member, okay? And ulitin ko lang po ulit sa inyo, yung torsional buckling po is hindi natin i-discuss or hindi na po tayo mag-i-example ng torsional buckling. Kasi sabi ko nga sa inyo, kapag compression member, napaka-rare lang naman na gumamit ng cruciform shape as compression member. So, mag-move on agad tayo sa Flexural-Torsional buckling. Okay? So, this is our introduction for overall buckling of compression member. So, thank you for watching. Bye!